Hey everybody, welcome to another video solution. Today I'm going to be going over the question 36 of the chapter 4 bingo problems. And this question is really interesting. It says, an advertisement claims that a particular automobile can stop on a dime. What net force would be necessary to stop an 850 kilogram automobile traveling initially at 45 kilometers per hour in a distance equal to the diameter of a dime, which is 1.8 centimeters. So this is a really interesting question because, we use phrases like stop on a dime and things like that, but do we ever really do the physics to find out what that would really entail? So I really enjoy doing this problem and kind of figuring out what that would really mean in a literal sense. So I kind of wrote some things out to make things easier. First of all, the 1.8 centimeters, we need that to be in meters, so that equals 1.8 times 10 to the negative 2 meters. And then right here is some dimensional analysis because our velocity is given in kilometers per hour, and in order for it to be used in our equations, we need it to be in meters per second. So I did some dimensional analysis and everything cancels out, leaves us with meters per second, and that ends up equaling 12 and a half. So I think, I put this right here. And this is our diameter of a dime. So now that we've gotten our unit conversions out of the way so that everything's in the proper form and proper units, now we can start looking at the problem. So first of all, we need to find the acceleration of this car. And so what we do is we use this equation, and the acceleration equals the velocity squared. So it's going to be 12.5 squared over 2 times, and this is the distance, right? And we know that the distance is that diameter of the dime. So 1.8 times 10 to the negative 2. And so when we do this in the calculator, we end up with 4,340 meters per second squared. And of course, if you're looking at it as far as it being a negative acceleration, since it's in the opposite direction, you could use this as a negative. If you're looking at just the magnitude of the acceleration, which in this problem it doesn't really matter, you can just think of it as a magnitude with the absolute value. So we'll just leave it here. It's easier to work with a positive number, and in this situation it doesn't really matter since really we're after the distance. So now what we do is we have the acceleration of the car, or at least the magnitude of the acceleration, and we know the mass. So we can use the F equals ma to figure out the net force necessary to stop within that distance. So the force, which is our unknown, equals mass, which is 850 kilograms, times and that equals a really big number. Equals that equals over 3 million, over 3.5 million newtons of force that would be required to stop this car within that short distance of the diameter of a dime. Now, of course, we can shorten this to a scientific notation if we want to be, you know, 3.7 times 10 to the 6th Newton. You know, that just makes it a little easier to read and kind of get the idea of the magnitude of this force. So anyway, in conclusion, to kind of wrap up and summarize what we've done here, we took the mass of the car. Well, first of all, we needed to find the acceleration. So we used the velocity that we had to use dimensional analysis on to get it into the right units. The velocity squared over 2 times that distance. We did that. Once again, we had to also change the units since centimeters won't work within our equation. We change that to the meters, find the acceleration, or the magnitude of the acceleration at least, then use the force equals mass times acceleration to find the net force that would be necessary. So, you know, if people are going to look at the car commercial literally, you know, the car company might be in a little bit of trouble because there's not a car in existence that could stop in that period of time. But of course, we know that the saying "stop on a dime" is more of a figurative thing. So hopefully, no one thinks that they can stop that quickly in a real car. So anyway, that's how you do question 36 from the Chapter 4 problems. Hope to see you next time in the next video.